Hi folks, today I'm bringing you an extraordinary driver from Princeton Technology Corp, the model PT6351. This driver is capable of supporting 8 to 16 digits and 8 to 16 segments. This capability is due to the ability to configure the pins as a general purpose input-output pin, grids, or segments. Of course, this versatility makes extra care necessary during its initialization. In the datasheet, they mention that the PT6351 is compatible with the MEN12510F, which is already a good help, as we already have a video on the channel about this other driver. I also emphasized that these drivers are usually found in the top of the line brand and model devices, such as the Denon, Kenwood, Marantz, etc. We will use the driver in the standalone mode with the help of a tiny board, paying special attention to the oscillator at the end of this video. The method used with the small board is the same as in the previous videos where this type of adapter was also used. It involved creating a mirror image of the pins on each side of the driver for the breadboard. In this case, 4 groups of the 11 pins. Connecting so many wires may seem like a difficult task, but difficult task is nothing more than the sum of the small easy tasks. It does not seem and isn't complicated to connect wire by wire using the necessary column. It is important that the breadboard does not have the three-rated connectors. As you may have noticed, I always use wires of the maximum of the 0.5 millimeters, and for example, when I need to connect a transistor or a diode with the thicker pins, I always do one extension of it with a 0.5 millimeters wire, so as not to widen the connectors on the breadboard. I remind you that the method of the connecting the VFD should be considered as individual connection for each grid and segment, but always choosing either the code or the hardware as a fixed reference point. Therefore, I need to adapt the code to the VFD pinout or connect the driver wires to the VFD according to that the codes requires. We used a VFD from a recent video, the Futaba FV734GB, which was a phosphor implemented on the front glass. It already shows significant here on the 4 digits used for the clock and the counter. Unlike the previous videos, where two 12 volts and 24 volts DC-DC converters were used in series to obtain a value of the 36 volts. Here we only use a series of the 24 volts and 5 volts to avoid exceeding the driver VE voltage limit present on the datasheet, which is referenced as a less 35 volts. The brightness is lower but sufficient for this proof of concept, where the recommendations of the applied electronics will not be strictly followed. We did not, for example, respect the requirement that the crystal and the associated capacitors be as close as possible to the driver pins. Using longer wires than necessary does not contribute to noise immunity, nor does it prevent the voltage drops due with a longer pad. Again, this is just a proof of concept. Since the driver circuit operates with a negative voltage VE equal to less 35 volts DC, it is important to remember to do the reference from the filament to this voltage using 47 ohms resistor, for example. As promised, let us see how to meet the need for an external oscillator for the driver. The datasheet mentions a 4 MHz crystal oscillator. Typical, the oscillators used on these applications, which don't require much special care, are ceramic resonators, like the ones I show here. Note that they come with and without a center pin. The center pin is simply the ends of the associated capacitors, which should be connected to the GND. Note that this example where I use a crystal, I connect the two capacitors to the crystal pins, while the other ends of the capacitors go to the GND. Remember that you can use both methods to provide the necessary oscillator for the driver. And if you want to follow the rules, just connect the crystal and capacitors direct to the pins of the tiny board. I would like to point out the datasheet used for the ceramic resonator, the attention drawn to the TTL and CMOS levels of the existing models. In this case, we used a MG model. We won't delve too deeply into code used to animate VFD, as the video will stay long and we already have many examples of how to control grids and segments. I only ask you observe the init function of the PT6351 to define the type of the VFD you will use. Remember that it can be any VFD with more or fewer grids or segments. You just need to connect the driver pins to the VFD pins and define the number of the grids and segments in the code.